In this section, we'll talk about trigonometric identities. Just like people can have different identities, for example, I'm a teacher, I'm a mom, I'm a wife, I'm a sister, and a daughter. Trigonometric identities also have different ways that they can be represented, and some of those ways we've already seen and are known to us. For example, we have learned about the Pythagorean identities where cosine squared of an angle plus sine squared of an angle always equals 1. No matter what the angle that you put in, if you take the cosine and you square it, then take the sine and square it, it will equal 1. The variations of the Pythagorean identity we came about by dividing either by cosine squared theta on both sides or by sine squared theta on both sides. So those are just variations of the Pythagorean identity. We've also seen the reciprocal identities where the sine of theta is equal to 1 over the cosecant of theta, or the cosecant of theta is equal to 1 over the sine of theta. This goes on for cosine and secant and tangent and cotangent. No matter what the angle is, these will be equal. The even and odd identities, where the cosine and the secant are even functions, and the sine, tangent, cosecant, and cotangent are odd functions. And finally, the quotient identities, where the tangent of any angle is always going to equal the sine of that angle over the cosine of that angle, or the cotangent of an angle is equal to the cosine of an angle divided by the sine of that angle. So what makes an identity different from just a regular old equation? Well, let's take a look. We will compare in this example an identity versus an equation. So an identity is true for any input, and an equation is not true for any input. Here's an example. We have said that the Pythagorean identity is an identity, and we know that the Pythagorean identity is cosine squared of some angle plus sine squared of that same angle, and that equals 1. So let's test it out. If we let theta equal, let's say, pi over 3, and we put pi over 3 in for our angle, then what we can do is actually find the cosine of pi over 3. Now the cosine of pi over 3 is 1/2, and I will square it. And the sine of pi over 3 is the square root of 3 over 2, and I will square that. And I'm checking to see, does this equal 1? Well, 1/2 times 1/2 is 1/4. Square root of 3 over 2 times itself is 3/4. This is feeling pretty good. And 1/4 plus 3/4 is 1. So sure enough, that works. We could try that for any other angle and it would still always be true. No matter what the input, the output is always going to equal 1. Now, let's look at an example of an equation. For example, the equation 2x plus 3 is equal to 1. Does it matter what x value we put in there? If I put in any x value in there, will it always equal 1? And the answer is no. And we know that because if we try to solve this equation, 2x plus 3 equals 1, by isolating the x variable, we get 2x is equal to -2. And when I divide both sides by 2, I get x equals -1. So this equation is only true for that one value of x. It is not true for anything else. I think one way to maybe convince ourselves of what we just saw algebraically is also by looking at the graph. For the identity where we looked at cosine squared of an angle plus sine squared of an angle equals 1, so the Pythagorean identity, we said that this is an identity because it is always true. No matter what we put in for x, no matter what we put in for x. So if let's say x was pi over 2, the output is 1. If I put in pi, the output is 1. If I put in negative 3 pi over 2, the output is 1. It's always 1. Compare that to the equation that we looked at. 2x plus 3 equals 1. The only time that we see an output of 1, is at this point right here, and that point is the point negative 1 comma 1, which proves that the only time this is a true statement is for that one particular value of x equals negative 1.